Welcome back to Next Gen Manufacturing Nexus. Today, we're on the hunt for a hidden enemy. It's an adversary so small it's invisible to the naked eye, but it's powerful enough to cause catastrophic failure in some of the most advanced machines on Earth. We're talking about microscopic imperfections that have massive consequences. So seriously, think about this for a second. What kind of tiny, hidden flaw buried deep inside a critical engine part could possibly have the power to compromise the safety of a modern aircraft? Well, the answer is a phenomenon called porosity, and the race to defeat it is driving a full-blown revolution in how we make things. All right, so this enemy we're hunting, it has a name, porosity. It's a silent threat, a hidden weakness that engineers are in a constant battle with, always trying to design it out and eliminate it from high-performance materials. To put it simply, porosity is all about the tiny, empty gaps or voids inside something that's supposed to be solid. A good way to picture it is like a sponge, but on a microscopic scale, trapped inside a solid block of metal. And you can see it right here. Over on the left, you've got a solid, dependable material, strong and reliable. But as you move to the right, you start to see those gaps, those voids. And these aren't just empty space, nope. They're actually points of weakness, the starting line for cracks, the origin of a potential failure. And that is the heart of the problem. You know, in high-stakes applications like aerospace, where parts are pushed to their absolute limits, microporosity isn't just some small quality issue. It's a critical safety flaw that can dramatically shorten a component's life. So you might be wondering, how do these little voids even show up in the first place? Well, it all comes down to chemistry and physics. When metal is molten, like a liquid, it can easily dissolve a ton of hydrogen gas. But check out that huge drop on the graph. The second that metal starts to solidify, its ability to hold on to that hydrogen just tanks. The gas literally rushes out, and if the metal cools down too fast, those bubbles get trapped. Bam! You've got pores. And where's all this hydrogen coming from? You'd be surprised. It's literally all around us. We're talking about moisture just hanging in the humid air, tiny bits of oil or grease. Even the super thin oxide layer that naturally forms on metal can trap water and introduce hydrogen. The enemy really is everywhere. Okay, so if these flaws are microscopic and buried deep inside a solid chunk of metal, how in the world do you find them before something goes terribly wrong? This brings us to the massive challenge of detection. The go-to tool for this job is something called X-ray computed tomography, or XCT for short. Think of it like a super-powered CT scan, but for engine parts instead of people. It lets us see right inside a component and build a full 3D digital map of everything going on in there, revealing every single hidden flaw. But, and this is a big but, here's the major bottleneck. You've got a human inspector who has to sit there and painstakingly go through thousands of these digital X-ray slices, trying to spot these tiny, weirdly shaped defects. It's incredibly slow, it's expensive, and let's be honest, it's the perfect recipe for human error to sneak in. And that's where things get really interesting. That manual bottleneck is exactly where modern tech comes in to save the day. We're talking about bringing in an AI to take over the hunt, doing it with superhuman speed and accuracy. Now, hold on, because not just any AI will do. A 2D AI, for example, is like someone flipping through a stack of photos one by one. It sees each X-ray slice on its own and kind of loses the context between them. But a 3D AI, like the 3D UNet model from Stanford researchers, sees the entire volume all at once. It connects the dots from one layer to the next, understanding the true complex shape of the flaw. So, the big question is, just how good is this thing? Well, in tests, this 3D AI scored a mean intersection of union value of 88.4%. Now that sounds technical, but what it's really measuring is how perfectly the AI's prediction of a flaw shape overlaps with the actual flaw. 100% would be a perfect match. So 88.4%, what does that mean in the real world? It's basically an A-. That's the grade this AI gets for automatically finding and mapping these incredibly tiny, hidden defects. For a manufacturer, this is huge. It means faster, cheaper, and way more reliable inspection. It's how you make sure a bad part never, ever leaves the factory. Okay, so finding flaws with AI, that's a massive leap forward. But the real endgame here isn't just about getting better at catching mistakes. It's about preventing those mistakes from ever happening in the first place. This is where we shift from just finding defects to designing them out completely. Right, this is the next frontier. Imagine this. Instead of just finding defects after the fact, what if you could predict them using a simulation? By using powerful models that simulate things like heat flow, like the dimensionless Niyama model, we can predict exactly where porosity is going to form before we even pour a single drop of metal. It's all about designing perfection right from the very beginning. And to prove this could actually work, researchers started with a digital blueprint. That's the CAD model you see on the left. Then they brought it into the real world, creating this physical mold, glowing hot and ready for casting on the right. And here it is. This is the big wow moment. On the top of each of these pairs, you're looking at the actual measured porosity from the real-world experiment. And on the bottom, that's what the simulation predicted would happen. Just look at how closely they match up. The model knew exactly where the weak spots were going to be. This is a total game changer. So when you have this kind of predictive power, you can test out different designs digitally without wasting time or money. So on the left, you see a thin plate with no taper, and yeah, it shows a lot of porosity, just like the simulation said it would. But check this out. On the right, by making the part a little thicker and adding a taper, the defects almost completely vanish. And they figured this out without making a single physical prototype. And the data backs us up completely. This graph makes it crystal clear. As you increase the casting thickness and introduce a taper, that percentage of porosity just plummets. It's a solid engineering principle, now proven and quantified with both simulation and real-world experiments. So, let's put it all together. What happens when you combine these two incredible breakthroughs, the AI inspector and the predictive simulation? Well, you don't just get a better process, you create an entirely new, smarter way to manufacture things. What you end up with is this intelligent, continuous feedback loop. It works like this. First, you design and simulate to get rid of flaws before you even start. Step 2, you manufacture the part. Step 3, the AI inspector gives you a super fast, super accurate quality check. And here's the magic part, Step 4. All that real-world data gets fed right back into the system to make the next simulation even smarter. It's a cycle of constant improvement, all driven by data. And all of this brings us to one final, pretty exciting thought. We are right on the edge of a future where we can design and build parts with almost perfect certainty about their quality. So my question to you is, if we can finally conquer the hidden flaw, what's the next frontier? What new levels of performance, complexity, and efficiency are we about to unlock?